Hello, good morning everyone, and welcome to this second day of the conference in the honor of Emmanuel. And we have a pleasure to listen to Timothy BUDD, who will talk about a bijection between rigid and integer labeled quadrangulations. Please, the floor is yours.
Okay, thanks a lot. So I'm greatly honored to speak in the celebration of Emmanuel's work. So I was a postdoc here in 2017 for a year, and Emmanuel was my host. And even though we did not publish together, I really took away Emmanuel's keen eye for bijections, and I will continue this theme here. I hope you will enjoy this little bijection, which is still a bit mysterious to me. So since this is a birthday conference, I thought let me try to find some cheesy pictures of the time that I was here, but I could not find anyone that included Emmanuel. For instance, of the time that I once again crashed my bike trying to bike up the plateau, and Emmanuel would come to pick me up and drive me to the bike repair shop, so thanks again. So this showed my typical Dutch background. As a matter of fact, I became Dutch while I was here as a postdoc, and I found a cheesy picture there. So this is me at the Dutch embassy in Paris, receiving my Dutch nationality. Now you may wonder, okay, why do I show this picture? Except that, okay, there is this nice Dutch ambassador in the royal family, but there was actually another character present approving of me getting the Dutch nationality who is relevant for this conference, because if you squint, up there, it's Descartes. Okay, joking aside, so there will be two main characters, both are planar maps, and they will feature in this bijection. So I don't think I need to go for all the definitions of a planar map, since they are already present in Mireille's talk yesterday, also Gregory, and the morning talks featured planar maps. So let's just agree that a planar map is a graph properly embedded in the sphere. I will mainly look at quadrangulations, so maps with faces of degree 4. And okay, sometimes it's useful, especially coming from a physics background, to think of these as gluing prescriptions of little unit squares in the Euclidean plane to turn it really into a piecewise linear manifold, although rarely we actually use this perspective. We will root our planar maps. So in Mireille's talk, there was a distinguished corner. I would take a distinguished oriented edge, but it comes down to the same thing. I will also consider maps on a disk, or if you like, near quadrangulations in the terminology of Mireille, where we allow one of the faces to not be of degree 4, and we really think of the contour of this face as the boundary of a disk. And for a quadrangulation, the boundary of the disk will always have even length, as you can easily prove. Now, there are many ways of attacking the enumeration problem of planar maps, but as I already alluded to, we're going to focus on the bijective method, so trying to find a bijection between the current family of maps at hand with another family that we already know how to count. And what I'd like to emphasize, and definitely something that Emmanuel has demonstrated to us to be a very powerful method, is that it gives you a lot more than just enumeration results. It allows you to relate statistics, say in one family, to statistics in another family, for instance. It allows you to describe or sample a random planar map by sampling, say, one uniformly on one side and then applying the bijection to get a uniform map on the other side. So there are many more reasons that actually having a bijection at hand gives you more than just enumeration. So what are the two characters of maps that will relate? So the first character is that of integer labeled quadrangulations. And here I'm following the presentation in the recent paper of Mireille and Andrew Elvey Price. So we're going to look at quadrangulations of the sphere whose vertices are labeled by integers, and it should be a proper labeling in the sense that neighboring vertices differ by exactly 1 in label. And then there is an additional constraint that my root edge points from label 1 to label 0. Otherwise, we could just shift all labels by an arbitrary integer, and we would have too big of a family. Okay? But with this constraint, you can convince yourself that there are only finitely many proper integer labelings of a given map. So this is the labeled part. You can also convince yourself that in a quadrangulation, if you look at the labels around the face, there are essentially 2 options. You can have an alternating label, so for instance 0, 1, 0, 1, or you can have a label that increases, increases again, and then decreases, decreases. And the terminology in the literature is that this is a colorful labeling. So why do we call this a colorful? Because there is actually a different way of characterizing this additional structure, where we view the labels modulo 3 and think of them as a 3 coloring of the vertices. So you can check that if you know the labels modulo 3, then actually that gives you the full labeling for free. And in that case, colorful really means that every quadrangle sees all colors. Okay? So we will forbid the alternating faces, look only at the colorful labelings of these quadrangulations. Now, as discussed in their paper, there are various other families of maps that are naturally in bijection with these. For instance, one can use the type of Schaefer bijection or Miamont or AB, don't know who AB are, where you look at every face of the quadrangulation, you draw a new red edge according to this type of Schaefer rule. And then if you do this for all the faces in the quadrangulation, actually what you get is a general planar map which is still properly labeled. Okay, so an integer labeling of general planar maps, and one can go back and forth here. So this is another way of seeing colorful labeled quadrangulations. Yet another character you can get by looking at the dual of this labeled planar map. So I put a vertex in every face. I connect 2 vertices if the faces share an edge. And then I orient the edge in such a way that the lower label sits to the right of that edge. Okay? And what you get is, again, a general planar map, but together with an orientation. And the orientation is such that you have an equal number of outgoing and ingoing sides, edges. So this is really a planar Eulerian orientation. Okay. So some history about the enumeration of these maps.
Timothy, I have a question. Is it your bijection is only for colorful quadrangulation, or it's?
So this is restricted to colorful quadrangulations. If you look, also include these alternating quadrangles, then you would get here integer labeled maps where labels are also allowed to remain constant.
Okay, thank you.
Yeah. And you will get partial orientations in the dual. Yeah. So this is all very nicely explained in the paper. But we'll focus exclusively on the colorful setting. So some history, even though I think it was not really realized at the time, these are actually special cases of maps, families of maps that are enumerated by matrix models. So in particular the ABAB matrix model and the 6-vertex model, which were both solved through matrix model techniques around 99 and then 2000. So there is definitely a link also with this area. So I think the first time the enumeration was attacked really in the combinatorics literature was by Mireille and collaborators in this paper, where they found explicit families of maps that kind of bound the enumeration of these labeled quadrangulations. And then Andrew Elvey Price and Tony Gutman in 2017, they actually found an elaborate system of functional equations for the generating functions of these maps. And based on this, they conjectured the asymptotic enumeration. And soon after, Andrew and Mireille found, I think, a slightly simpler set of functional equations that they managed to solve by guess and check methods. So here is their result, or at least a special case of their result for these colorful quadrangulations, that their generating function can be expressed in terms of a solution of this power series equation. Okay. Then actually Andrew continued, Paulsen just then, to revisit the solution of the 6-vertex model in a rigorous fashion. And very recently, there was another paper by Mireille and Andrew where they actually enumerate these objects with finer control. For instance, on the number of local maxima of the labeling, which will return in a later point. Okay? So if you look at their general solution, they also state the asymptotics for the number of these labeled quadrangulations when the number n of faces increases. And then it grows exponentially with 4 pi to the power n, and there is a power law correction, n to the minus 2, and also a logarithmic correction. And if we think back to the first talk of this workshop by Bertrand, we know that the exponent in the power law correction, it should be universal and tell us something about what these maps look like in the large n limit. If you look at, for instance, uniform triangulations or uniform quadrangulations, then it's well known that this exponent will be 5/2. And as Gregory explained to us, the scaling limit of many families of planar maps is that of the Brownian sphere. But if we decorate maps with various statistical systems, like decorations by a spanning tree, then we can get different exponents. And it's expected, and certainly partial results are known in the literature, that there is a one-parameter family of random metric spaces in the continuum limit described by Liouville quantum gravity. And the parameter of this one parameter family of Liouville quantum gravities is related to this exponent, and basically this is the KPZ equation that Bertrand already showed. Okay? But not in terms of the central charge, so here I write it in terms of the Liouville coupling of the Liouville quantum gravity. So if we now compare the alpha equal to 2 to this formula, then what we see is that it should correspond, or this we should predict, that it corresponds to gamma equal to 2, which is the maximal value of the coupling that it can take in Liouville. So this is known as the critical Liouville. Physicists will think of this as the C equal to 1 barrier, or two-dimensional quantum gravity coupled to a scalar field, because we can think of these labels essentially as a Gaussian free field in the limit living on top of the geometry. Okay. So even though these can be thought of as colored quadrangulations, and yesterday we saw colored triangulations, but actually they live in a rather different universality class, supposedly. Okay? So it would be useful to understand these better. And also, if you look at these little pictures of the various random planar map models, something you will notice is that they become progressively rougher, more fractal, when we either decrease the exponent alpha or increase the gamma parameter. So we should really think of that these types of maps are kind of maximally rough within this family.
What about log square n? Log square n?
Yes, so this should be related to the fact that it's critical, so that it falls outside of the usual family, and you get additional logarithmic corrections. Not as far as I know.
So it's not KPZ formula.
But okay. But the KPZ formula, it predicts just the exponent. It just says nothing about the exponent of the logarithm, as far as I know. Okay, so that was one character. The other character is rather different. So now let's look at the geometries that are not randomly curved, but are flat. So what do I mean by flat? Well, think of a metric, in this case on a disk, that is locally isometric to the Euclidean plane. That means that we can immerse this geometry in the Euclidean plane, but it may not be an embedding. Right? So here is a flat metric on a disk. I immerse it, and I see that the disk will overlap when I immerse. Another way to think of this is a generalized polygon, in this case, in the Euclidean plane, that I can get by gluing polygons together in an arbitrary fashion, as long as I keep a disk topology. So I will be looking at rectilinear disks, meaning that the boundary of the disk becomes a piecewise orthogonal curve in the Euclidean plane. So suppose we would like to understand the family of all these rectilinear disks. Then locally we can parameterize them by specifying the side lengths of the disk. I need to specify, if I have two n sides, 2n minus 2 of them, because the last two sides will be determined. Okay. So that means that the moduli space of rectilinear disk is naturally equipped, say, with the Lebesgue measure on the independent side lengths.
Sorry. Don't you have also to decide about the direction where you turn at each angle?
Yeah, so I will get to this. So locally I can vary the geometry by changing the side lengths, but there is a combinatorics underlying this. So let me describe this. So in particular we can make sense of kind of a uniform rectilinear disk of fixed perimeter. But let's now look at a generic so a Lebesgue typical disk. I can actually see that there is combinatorics underlying this by looking at all the right turns where I have an angle of 3 pi over 2. I shoot a ray in both directions coming from this corner, and actually it tiles my rectilinear disk with rectangles. Okay? And the combinatorics of this tiling, which is really just a quadrangulation, I call a rigid quadrangulation. And what one can notice is that in order to specify a generic disk, I have to specify the combinatorics of the quadrangulation. And then for each of the columns and rows of this tiling, I specify the width. And the perimeter of the disk will just be twice the sum of all the widths. So really this continuous aspect to it is rather boring. If I want to sample a uniform rectilinear disk, I just have to sample a uniform rigid quadrangulation and then just distribute my perimeter in the various columns and rows by sampling a point in the simplex of dimension 2n minus 2. So really this is just combinatorics and it's not geometry. Okay. So what is really a rigid quadrangulation? So it's a quadrangulation in the sense of the disk, in the sense that it has one face that is not a quadrangle. Every inner vertex that is not on the boundary is supposed to have degree 4, making it flat. And then the boundary vertices come in 3 types. We have a convex vertex where I have an angle pi over 2, straight boundary vertex with an angle pi, and then a concave vertex with angle 3 pi over 2. And there is one additional restriction, and this is related to just looking at rectilinear disks in general positions, so generic ones. And that is that all the inner edges of the quadrangulation, they partition into rays, and those rays will always start at a concave vertex and end at a straight one.
Excuse me.
Yes.
So could you
Yes, indeed. So by definition, I now orient all the edges away from the concave vertex. So I actually use this decoration because it will come in handy later, but you can recover it. Yeah. Okay? And then finally, I said we have to root maps. So I will, by convention, root it on a corner that has to be a convex vertex. So then the main bijective result that I would like to describe for you is that these rigid quadrangulations with n+1 convex vertices are in bijection with colorful quadrangulations with n vertices. Now actually, in this setting, it's a 1-to-2 map. So there's a slight ambiguity in the root face of the colorful quadrangulation. So to make the bijection, I have to require that the root face has labels 0, 1, 2 instead of -1, 0, 1. So there are only two options, and they're related by symmetry. Okay. So let's have a look at this bijection. So here's an example of a rigid quadrangulation mapped to a colorful quadrangulation. Now I said the number of vertices on this side corresponds to the number of convex corners except for the root corner. So let's just identify these convex corners with the vertices on the map. And for this, I first have to tell what are the labels of these corners. So the prescription is that I start at the root corner, and then I follow the boundary in counterclockwise order, and I just count the number of left turns minus the number of right turns. So this is the turning number of the boundary, or the winding number, if you like. Right, so here, the first corner I encounter, I've made no turns, so I get a 0. Then 1 left turn, 1 right turn, so I'm at 0. Here I have another left turn, so I'm at 1. Then 3 right turns, so I'm at -1. Okay, because I had a left turn here, and then 3 right turns, etc. Okay? Now these vertices, they should be points on the sphere, because I want to build a planar map. So how can I think of them as points in the sphere? Well, I take my polygon and I double it. So I take 2 copies of the polygon and I glue them along the whole boundary. So that gives me a topological sphere with my corners being points on the sphere and then a Hamiltonian cycle. Okay, so let me forget about the Hamiltonian cycle. What I need to do to turn this into a planar map is now draw all the edges. And I can equivalently draw the edges on this side, but I have to tell you where they are living. Are they living on the front or the back of the disk? So the prescription is actually not too complicated. I need to draw an edge for every row and column of the rigid quadrangulation. So here is an example. I have a row. So I want to draw an edge that traverses the whole row, but it has to connect up to one of those convex vertices. So essentially, I do the simplest thing to find a convex vertex. What I need to do is I need to note that if I have a row, it separates the disks into 2 parts, and one of those parts will contain the root of the disk. So this gives a natural transverse orientation to the row, in this case upward. And then the algorithm is to follow the row until you hit the boundary, then turn up until you hit the boundary, turn right, turn up, turn right, until you encounter a top right corner. And then in the other direction, I go to the left, I hit the boundary, I go up, I go left, I go up until I find the top left corner. Okay? So in this particular example, I go left, I have to go up, and I find this one. So I need to do this both for the rows and the columns. So here's one for the column. So now the root is to the right, so I have to orient it to the left. I go up to the left, up, and I find this one. And here I need to go down and to the left, and I find that one. But I want this to be a planar map, so the edges should not intersect. But this is easy to ensure because I just make the prescription that I travel horizontally on the back of the disk and vertically on the front of the disk. Okay, so then these two edges actually do not intersect each other. Let's do another one. So for this row, I have to orient upwards, so turn up. I find this one, and I find that vertex. And now you may complain because actually in the way I draw it, these edges, they touch each other. But really what is happening is that these edges, they merge and end on the same vertex. So I could really turn it into topologically it looks like this. I have an edge, and then before reaching its endpoint, it merges with another edge that goes there. But I can slightly pull them apart to make them really non-intersecting. Or if you prefer, I draw all my edges, and whenever two edges are on top of each other, I just contract all points to a single point. Topology. Okay? Okay, so I do that for all rows and columns, and I get a figure like this. And then, well, you'll have to stare at it for a while to see that I can deform it into this picture, which was the original quadrangulation. Okay. Now, one thing you can observe is that certainly this is going to be a properly integer labeled map, exactly because of the prescription where I go from, here for instance, I connect a top right corner to a top left corner, and then I know that in between the number of left and right turns will be equal due to the flatness constraint of the quadrangulation. So it's certainly integer labeled, but it's actually not at all obvious that it's a quadrangulation, nor that it's colorful, and certainly it's not clear why it's bijective. And maybe I can leave this as a puzzle. Actually, it's a fun thing to do. You take a piece of paper, you cut out a nice orthogonal polygon, and then just draw this literally on the front and the back. It's actually a nice exercise. Okay. But one thing I want you to take away from this explicit prescription of the bijection is a nice symmetry, because if I flip this rectilinear disk, or the rigid quadrangulation, in the diagonal, then nothing changes in the edges. The only thing that changes is the labels, because I said we traverse in counterclockwise direction. Now it becomes clockwise. So it means that I'm shifting the labels to 2 minus the label. And why is it very useful to have this here? Because the way I'm going to prove the bijection, it will completely destroy this symmetry. So certain statistics that you would like to examine that are naturally symmetric, one has to rely on this symmetry to recover them after the fact. Or to put it a different way, the actual description of the bijection I will show in a minute, it seems a bit artificial. It's only when you realize afterwards that it respects the symmetry that it seems we have uncovered some deeper notion here. So I said there will be some statistics that are naturally mapped to each other. We've already seen a couple of them, but let's extend the dictionary a bit. So rows and columns, they correspond to the edges of the quadrangulation. One could be a bit more precise. So the rows correspond to even edges, meaning that the minimal label is even, and the columns the odd edges. The vertices in the quadrangulation, they are the convex corners that are not the root. The faces of the quadrangulation, they are naturally related to the concave vertices or to the root. And then one can actually understand more refined statistics regarding the labeling in a geometric way on the disk side by looking at shortest paths from the corners to the root corner. So here's one example. A natural statistic that was indeed studied by Mireille and Andrew is the number of local maxima of the labeling. But the local maximum corresponds on the disk side to the situation where the shortest path to the root, it follows the boundary in counterclockwise order. And the local minimum, by symmetry, follows the boundary in a clockwise direction. So here are two examples. And then clearly the vertices for which the shortest path leaves diagonally, they are neither local maxima nor minima. So another natural statistic to look at on the labeled map side are the level lines of the integer labels. So here is a level line that cuts through all the edges, or a set of edges with label 0, 1. They correspond to concave corners where the shortest path to the root leaves in one of the quadrants adjacent to the boundary. Right? So there are two options. Either it goes in counterclockwise direction or in clockwise direction, or that's the other way around, right? But it's not allowed to leave in the quadrant opposite to the boundary. Okay? So you can see there are actually 5 such concave corners in this example, corresponding to the 5 level lines here. There are 2 more level lines here that are not in correspondence with concave vertices, and those are the 2 level lines that go through the root face of the map. So we need to ignore those. Okay. Any questions here? Okay, so how do I prove this bijection? So the idea is to introduce a catalytic parameter, which is often very useful, and then use this catalytic parameter to explore the objects that we have via recursive decomposition. So it's useful to think of our rooted quadrangulations actually as a quadrangulation of the disk by opening up the root edge. So this will be a disk of perimeter 2, right, in this fashion. And similarly, on the rigid quadrangulation side, to add a little column in such a way that now my root is on a side of the disk that ends in a pair of convex corners. And I call this the base of the disk. And then the claim is that colorful quadrangulations of the disk of perimeter 2p, so the more general setting, are in bijection with rigid quadrangulations with a base of length p. So what is a colorful quadrangulation of the disk? Well, it should satisfy the same requirements as before, except that now I have a boundary and require that the labels along the boundary alternate between 0 and 1. So if we prove this more general bijection, then the previous one actually follows as a special case. And the way to do this is by identifying canonical explorations on both sides. So it will be a row by row exploration of the rigid quadrangulation and the peeling exploration on the labeled quadrangulation. So some of you may have seen peeling of maps before. So what is the general idea? We think of our map as being fully unexplored, and we start from the root face, so from the boundary, and then edge by edge and face by face reveal the interior of the map. So at the start, I only know the perimeter of the map, which is this 0, 1 alternatingly labeled cycle. And I ask to reveal what sits on the other side of the root edge. And there are essentially three options here, or let's say first two options. Either what sits on the other side of the root edge is actually another edge on the perimeter. So this is the tut-like decomposition that already appeared in Mireille's talk. Or what sits on the other side of the root edge is a quadrangle of my quadrangulation. Now the point is, so why does this tut-like decomposition work? It's because what sits in the unexplored now two regions is again a properly labeled quadrangulation with 0, 1 labels on the boundary. But if I reveal one of these quadrangles, it will either have labels 0, -1, 0, 1, or 0, 1, 2, 1. So the remaining part of the map will not have the appropriate boundary condition. So to really have a recursive decomposition with the catalytic parameter being the perimeter, is we need to reveal more. In fact, we need to reveal the full level line of 0, -1 here. So it will go through a sequence of quadrangles before returning to the first quadrangle that I revealed. And if I do this, then on the outside of this ring of quadrangles, I will again have the appropriate boundary condition. And inside, I will have a -1, -2 alternating boundary, inside of which there will be again an object of our type, but just with the label shifted by 2. Okay, sorry, by 2? By 3, right? No, by 2. By 2, yes. Okay, so in order to describe this single recursive step of the exploration, one needs to describe the event that happens, and if we reveal a quadrangle, we have to describe the sequence of quadrangles that are glued along the level line. Now there is a very similar recursive decomposition of the rigid quadrangulations, where now I look at the top of the first row above the base. And there are again three options. Either the top of this row hits the top of the disk, and then there will be two rigid quadrangulations on either side of this segment. Or the top of my first row corresponds to a ray that emanated from a concave vertex on the side, and then there is a decomposition of my disk where I have an unrevealed part downstairs and an unrevealed part upstairs. And to explain the exact possibilities, one has to keep track of the orientations of the rays that I encounter to the right of my base. Okay. Let me not go into any great detail here, but the general picture should be clear. The possibilities of the recursive decomposition for the rigid quadrangulation are exactly in bijection with the possibilities for the colored quadrangulation. So recursively, I can now construct a bijection between the two. So here is an example. I explore my rigid quadrangulation row by row, and I just perform the corresponding peeling step on the map, and then I iteratively construct the corresponding labeled quadrangulation. So the only thing that remains to prove the initial bijection is to explain the prescription of drawing edges of this map on top of the rigid quadrangulation. Let me not give the details, but one can actually track the vertices that sit at the end of an edge that I've explored throughout the exploration, and then find out what the final vertices are that correspond to them. Okay? There is some bookkeeping involved to do that. Yes?
If you did the exploration on the left-hand side using column by column, row by row, so it changes the peeling in each.
So the peeling exploration will be rather different, but the result will be the same exactly because of this symmetry. And this is where the magic is. Maybe it's a coincidence, but it's true. So I said in the abstract that I would give a little motivation, but I'm nearly out of time. So let me make the motivation very brief. So all of you may know that random planar maps are connected somehow to two-dimensional quantum gravity in the sense that it gives a natural way of describing a random metric. And a random metric gives a characterization of what a physicist would call the Euclidean path integral over metrics. Now in recent years there has been interest in essentially a somewhat simpler question where we're not looking for a random metric, so not a path integral over all Riemannian metrics that we can put on the surface, but Riemannian metrics with a constant curvature. And in particular, random hyperbolic metrics appear in JT gravity. And the question has been asked, is there a proper quantum JT gravity when we have boundaries present in the system? And in the physics literature, it has been investigated from many different angles, but most of them are actually focusing on the situation where the boundary is mildly fluctuating and close to being asymptotic in the sense that, okay, I'm not entirely sure how to explain. There have been several works in the physics literature asking, can we actually deal with this path integral in a situation where the boundaries are not asymptotic, so they're really at finite distance? People have played around with thinking of domains in the hyperbolic plane or in the Euclidean plane that are bounded by SLEs. Maybe those are good laws for random flat metrics. But Frank Ferrari recently proposed that no, we should be looking at the most general class of flat or hyperbolic metrics on disks that upon immersion correspond to self-overlapping curves in the plane. And he asked whether there is a tractable notion of discrete random flat disks. And so these rigid quadrangulations are an example of these. Now let me just flash that there is actually a different type of bijection one can give for flat disks. So if we relax the various constraints that made a quadrangulation with inner vertices of degree 4 a rigid quadrangulation and look at the most general class of flat quadrangulations where the boundary now can have arbitrary degrees, then it turns out that there is a bijection with walks in the half plane, excursions in the half plane, with a little constraint on the sub-excursions. And using this bijection, one can again solve the asymptotics and find that the asymptotics is really the same as for the rigid quadrangulations, making one expect that these two actually live in the same universality class. So here are little simulations of a uniform rigid quadrangulation and a uniform flat quadrangulation. And these are naturally related to random walks for large n, so we should expect them to be Brownian excursions in the half plane. And somehow these should relate to these critical Liouville quantum gravity type surfaces. Okay, so but there are some question marks remaining here. There's another simulation of a flat quadrangulation if I do not immerse it in the plane, but embed it in 3D. So it gives you a sense of the fractal boundary that we have, even though in the interior it's perfectly flat. Okay, so there are some perspectives. One can make some predictions for what the construction in the continuum limit would be. But let me stop here leave up the questions for Emmanuel. So there are many combinatorial questions we can address here. And thank all of you for the opportunity.
Thank you, Timothy. So maybe in view of time, we have time for one or two short questions. Let's play this game.
Yeah, so can you use this to do any computations to match statistics for the level lines on your maps to CLE4 on critical level quantum gravity?
Well, I mean, this is a good question, and I've not done it. So the first thing one can do is ask for the label of a uniform vertex in the colorful quadrangulation. So this is a problem that Andrew has been working on. And it relates to the winding number of the boundary. Then the next natural question would be to ask about correlations between the winding on the boundary of this disk. And there maybe actually the disk perspective would help over the labeled quadrangulation perspective. But all of these questions are still open and need work.
But do you know anything about like the size of the faces as you're doing your peeling? Because you're kind of discovering
Yes,
like the
yeah. I mean, the peeling exploration that I showed, it's essentially of the type of the peeling of the gasket of the O2 loop model on a planar map. So relating this to the self-similar Markov processes there, I mean, this should be relatively straightforward. And we don't expect anything new to happen.
Yeah. Okay.
And it tells us something about the width of the disk as I scan it only upwards.
Okay, thank you.
One more question, if any.
What about triangulation? What is special about the fact that we're dealing with rectangles? For example, if I'm talking about triangulation, we should expect the same result?
Yeah, so in fact, the result that I quoted using a bijection with excursions in the half plane, this works for a large class of flat maps, including flat triangulations. And the scaling is the same. Yeah. But yeah, so what is mysterious is that only for the rigid quadrangulation do we know of a relation with these labeled maps. So I'd be very curious to hear if someone can find variants of this bijection. Generalizations would be even better, but.
Okay, so thank you very much. Thanks, Timothy, again.